everybody! In this video, we're going to be talking about formal proofs of arithmetic statements, which really just means that we're going to be talking about number theory. And so with that, we want to think about the things that we learned about with modular arithmetic and start to see different applications of them. So just as a quick review, we have here those definitions, which is if you have an integer x, you can divide it with d, and then you can write it in terms of x is equal to d times q plus r. And we say r because it's the remainder, and we call it q because it's the quotient. The other thing that's pretty helpful here is thinking about the rules of modular arithmetic. So we have that if you add the numbers together inside the mod, then you can split up that addition and then mod it again, and you will get the same result. So number theory has these applications where we're going to use the sum rule and this similar product rule in order to prove certain things. Later on, we'll see one of the main use cases is going to be for cryptography. So the first thing that I want to talk about in terms of number theory is thinking about the greatest common divisor. So if I have x and y, and those are two positive integers, then the greatest common divisor is the number that is the largest between the two of them that divides both. So what I'm showing here, though, is we have this algorithm where I'm going to continue to apply mod to the larger number until I get to 0. If I keep applying this algorithm, eventually the algorithm is left with 0 and another number, and whatever that other number is the GCD. So let's take a look at an example. I have two examples here. One is GCD of 15 and 6. And so thinking about that in terms of 15 is equal to 3 times 5 and 6 is equal to 3 times 2, we can see that the GCD is going to be 3. Let's go ahead and apply our algorithm to see if that works. The first thing is I'm going to do this kind of flip where I take that second number and push it into the first position because it's y mod x. So this ends up being GCD of 16 mod 15. And 15, which is a little bit silly because it's just 6. But that's going to get me GCD of 6 and 15. And that's just to get the order right. Then next I'm going to do GCD of 15 mod 6 and 6, which is going to be GCD of 3 and 6. And then again, I'm going to do that thing where I take that second number and then push it into the first position modded by the first number. So that's going to be GCD of 6 mod 3 and 3, which is GCD of 0 and 3. And as I said earlier, the algorithm is going to be left with 0 and another number. That other number is the GCD, so that is 3. And that's what we expected to get. I have one more example here, which is the GCD of 7 and 13. And so thinking about that, I will have GCD of 13 mod 7 and 7, which is going to give me GCD of 6 and 7. That will end up being GCD of 7 mod 6 and 6, which is GCD of 1 and 6. And then I'm going to do GCD of 6 mod 1 and 1, which is going to give me GCD of 0 and 1, which is 1. And so this makes sense because I have these two prime numbers, and with prime numbers, the GCD is always going to be 1 between the two of them. This algorithm that I've been running, because I am running an algorithm, I'm going step by step, is called Euclid's algorithm. And so the idea here is that the GCD of A and B can be shrunk down into the GCD of B, A mod B, and then eventually when you get to 0, the GCD is just going to be whatever A is. So keeping that in mind, with Euclid's algorithm, we are now going to move on to the extended Euclidean algorithm. With just the Euclidean algorithm, we use that to get the GCD, or the greatest common denominator. The extended Euclidean algorithm is going to find me these numbers s and t, where the GCD of x and y is equal to s times x plus t times y. In other words, you get a linear combination of x and y. Let's look at some examples. And so I have the GCD, remember from the previous page, of 15 and 6. And as we were working through that GCD, we had 15 mod 6, which is 3, and 6. And then we had that was 3, so I had 6 mod 3 and 3, which we can remember just from that previous page there. Right, so we were keeping track of these things throughout. So when I think about 15 and 15 mod 6, we can see that 15 is equal to 6 times 2 plus 3. Well, nicely for us, 3 is the GCD that we wanted. It's also a remainder. And then 6 and 15 are the two numbers I want to write a linear combination of. We are going to rewrite this as s times 15 plus t times 6 is equal to 3, based on this definition of the extended Euclidean algorithm. And then I can see that 3 is equal to 15 minus 6 times 2, which I can then rewrite to say, well, it's 1 times 15 plus minus 2 times 6, which is equal to 3. And that's exactly what I wanted from this GCD definition above, of extended Euclidean algorithm. So I have that s, if I have x is 15 and y is 6, then it's going to be the case that s is 1 and t is -2. Looking at the other example, because we had GCD of 7 and 13, we had then 13 mod 7 and 7. And then I had to take another step, which was 7 mod 6 and 6. And then going back up, I had to have 6 mod 1 and 1. All right, so recalling that, we want to rewrite my equation as s times 7 plus t times 13 is equal to 1, which is my GCD. So how are we going to go about doing that? Here is the place that I have that mod 1. So I know that 6 is just equal to 6 times 1. And then I have that 7 is going to be equal to 1 times 6 plus 1. All right, we're still not quite there yet because I don't have 13, but 13 is equal to 7 times 1 plus 6. We need to combine these equations together, and what's going to happen is as we do that, we're going to back substitute where this 6 can be back substituted into this 6, so it's 13 minus 7. And what will eventually happen if you follow that along, you are going to get 2 times 7 plus -1 times 13. And that is, in fact, equal to 1. And so you get the idea that with extended Euclidean algorithm, I need to keep track of not just the remainders, which is what I was doing with just Euclidean algorithm, but also keeping track of those quotients. The next really important idea in numbers is the fundamental theorem of arithmetic. This theorem is every positive integer other than 1 can be expressed uniquely as a product of prime numbers when the prime factors are written in non-decreasing order. So taking a look at a couple of examples, I have 6. I'm going to write that as 2 times 3. Next, I have 19. Well, 19 is prime, so this is literally just 19. 18 is going to be 2 times 9, but that's not prime factored, so it's going to be 2 times 3 times 3. 82 is 2 times 41. So a couple of reminders. 2 is a prime. It's our only even prime. And then 1 is not included. When I put these ideas together with the fundamental theorem of arithmetic and that extended Euclidean algorithm, I can start to talk about something called Bézout's identity. So with Bézout's identity, it's exactly what we did with the extended Euclidean algorithm. It's just I have this proof here. If I have 2 numbers, then I can find 2 other numbers and write it as a linear combination am plus bn is equal to GCD of mn. And I have here the proof, which rather than writing out, I have typed just to make it a little bit quicker. You would not be expected to know this proof, but we do want you to be able to think about numbers GCD and what the linear combination would be. All right, so let's walk through this. If I have my 2 numbers, m and n, I want to make sure at least one is not 0, and then let's say the GCD is given by the variable d. Then let's set this set x to be x being some positive integer, and x is equal to am plus bn. And so here, one thing I'd like to point out is there are actually infinitely many combinations for m and n, but what we're looking for is specifically the GCD. Note that S is non-empty because if m is greater than 0, then at least 1 times m plus 0 times n is in S. If m is less than 0, then negative 1 times m plus 0 times n is in S. And if m is equal to 0, then by assumption n is not equal to 0, and so 0 times m plus 1 times n is in S, or 0 times m plus negative 1 times n is in S. And so we're going to say, look, S is not the empty set. Now, because S is non-empty, then we can say that the numbers are going to be ordered in the set. So even though sets are unordered, we can write the elements of that set in an order, and we can say that there is a least element. And so by the definition of S, because of the numbers that are in it, I'm going to say C is equal to AM plus BN. Now, 1 and 2, these are the 2 things I'm going to have to prove. C is greater than or equal to D, and C is less than or equal to D. And so looking at that, when I have C greater than or equal to D, C less than or equal to D, it means, well, C must be equal to D. And that's going to be the conclusion that we're going to make. All right, looking at the cases, D divides C, therefore D is less than or equal to C. D is literally the GCD of M and N, and therefore by the definition of the greatest common divisor, D divides M and D divides N. That means M is equal to dx and N is equal to dy for some integer x and y. So then I write here, C is equal to AM plus BN, and then M and N by the definition of D are written as dx and dy, and then I'm going to take D and I am going to factor it out. I'm going to get D times, in parentheses, AX plus BY. I know that AX plus BY is an integer because it is the sum of products of integers, and so this is based on the closure properties of integers. And so therefore, by the definition of divisibility, D divides C. And both C and D are positive, and therefore C is greater than or equal to D. And that's what we wanted to show here. The other case is to show that C divides M and C divides N, and therefore C is less than or equal to the GCD of M and N. We're going to apply the division theorem, which means that we're going to rewrite M in terms of its quotient and remainder. So M is equal to C times Q plus R. When we subtract, we're going to get R is equal to M minus CQ. And that should feel familiar in the sense that we did it with the extended Euclidean algorithm. Now C is equal to AM plus BN, and so I'm going to just do some substitution. M minus, where I had C, I'm going to write AM plus BN, and then I'm going to rewrite that equation. Now R is a linear combination of M and N, and if R is greater than 0, R is an S, so R would be smaller than C in S, but that's not allowed because C is supposed to be the least element of S. That means R must be 0. By substitution of M is equal to CQ, we then see that C divides M. We can see by that same kind of argument that C divides N. C divides M and C divides N is a common divisor of M and N, so it must be less than or equal to D. And since we showed that C is less than or equal to D and C is greater than or equal to D, then it is concluded that C is equal to D. So now that we talked about Bézou's identity, it's going to be helpful to use that to see that two numbers are coprime if their GCD is 1. So remember that GCD is greatest common divisor, and if numbers have no prime factors in common, then their GCD will be 1. How do we actually prove that? Well, let's say we have two numbers, P and M, and they're supposed to be coprime. We want to show that the GCD of P and M will be 1. So thinking about that, let's say we have P, M, and N, and P divides M and N. But P and M are coprime. We need to show that P divides N only. Now, using Bézou's identity, we know that there is an A and a B, where A times P plus B times M is equal to 1, which is in fact the GCD of P and M. Let's multiply both sides of this equation by N. All right, so taking a look, I have AP plus BM is equal to 1. I multiply both sides by N. Now, I can see that NAP is a multiple of P, right? So P divides NAP because I can literally factor out P. And so that means that we can factor that out, and we have that P divides MN, so because we already know that by assumption, and then that means that P divides BMN. That means that P divides both NAP and NBM, which means P divides NAP plus NBM. Now, based on the way that this is written, we can then conclude that, in fact, P must divide N. And so kind of taking a look at that, I could rewrite this like that, but this is equal to 1, and so it must be P is not going to divide it, so it must be the case that P divides N. All right, finally, the very last thing is to talk about Fermat's little theorem. And so now with modular arithmetic, we had those rules where we said, how can we deal with multiplying and adding two numbers together? And we've dealt a lot with coprime and GCD already. So Fermat's little theorem, one way to state it is if I have P, which is prime, and I have any number M to the P minus M is equivalent to 0 mod P. Another way to state this is that if P is prime and M is an integer, M is not divisible by P, it turns out that M to the P minus 1 is equivalent to 1 mod P. And yet another way to state it is going to be for every integer M and Z, M to the P is equivalent to M mod P. Looking at 1 and 3 together, I have M to the P minus M is equivalent to 0 mod P, And so I know that if I add m to both sides, I would get m to the p is equivalent to m mod p. And so looking at that, you can see how 1 and 3 are equivalent. The kind of special one is where m is not divisible by p. I can write it in terms of m to the p minus 1 is equivalent to 1 mod p. Let's take a look at a small example where I say p is equal to 5 and m is equal to 4. And I already wrote it out, but if I have my equation m to the p minus m mod p, then I'm going to replace m here with 4, p is 5, and of course I'm going to do that mod 5, right? So remembering that 5 is equal to 2 plus 2 plus 1, and if I have exponents, I can rewrite it into the sum, which is multiplication in the base. And 4 to the 1 is, of course, just 4. And so here, this is 16. And I know that 16 mod 5, well, that's 15 plus 1. And 5 times 3 is 15, so this is equivalent to 1 mod 5. So I can say this is 1 times 4 minus 4 mod 5. And then 1 times 4 is, of course, 4. 4 minus 4 mod 5, which is equivalent to 0 mod 5, which is exactly what we wanted.